continuing these examples to part E. We're now going to get into some very fun theoretical stuff. The question now is to calculate the acceleration due to gravity on the surface of Earth. Now, you're watching this video, you've been in physics for a while, you know that the answer is 9.8 meters per second squared, because we've been using that for a while here. And we've even done some activities where we've measured this number, okay? We use different software to actually get that value because we, dropped an object and took a video of it and measured the position of that object over time, right? So we're pretty comfortable with this number and having specifically measured it. But this is one of the first times that I'm actually asking you to calculate the acceleration due to gravity. And the cool thing about this is, could you get this magic 9.8 meters per second squared just from the math, not actually measuring it? And the answer is yes, and this is how it works. We know from Newton's second law of motion, which states that force equals mass times acceleration, that if you were to rearrange that, you would get acceleration is force divided by mass, right? The acceleration on an object. And so with this kind of starting statement, let's think about this. Suppose you are dropping a ball on the surface of Earth, right? Then the acceleration that you would be measuring would be the acceleration due to gravity. And the force on the ball, assuming there's no air resistance, would be the force of gravity. And then the mass, I would say, is the mass of the whatever object it is. In this case, it's a ball, but you could be dropping a piano, you could be skydiving, you could be doing all sorts of things. So I'm just going to say this is the mass of the object. Okay, so for an object that's experiencing free fall, its acceleration will always be the force of gravity on it divided by its mass. Okay, so let's take an additional step. I'm going to put the mass of the object down here in the denominator. And what's new is this. We now have an equation to calculate the force of gravity on any object. And it's always the universal gravitational constant times the mass of the object times the mass of whatever planet or moon that object is on. In this case, it's on the Earth. Okay, this is my M1 and M2. And then I will always divide by the distance between the centers of those masses, right? The distance from the object to the center of the Earth. And so in this case, that would be the radius of Earth. And don't forget to square it. Okay, so I've got this like big thing in the numerator and then the mass of the object here in the denominator. Okay. Now notice that I've got some repeating items. I have the mass of the object on the bottom, which will cancel out with the mass of the object on top. And this is why we have learned previously that the mass of an object does not affect the rate at which it falls. You can see that it cancels out. And so this simplifies to big G times the mass of the Earth divided by the radius of Earth squared. Okay, that's it. So if you take those numbers, you get 6.67 times 10 to the negative 11. That's Newton's meters squared per kilogram squared. Times the mass of Earth, which is 6 times 10 to the 24 kilograms. And then divided by the radius of Earth, which is 6.4 times 10 to the 6 meters, squaring that. Now, check out the units. We've got meters squared on the bottom. That cancels out with this. We've got kilograms here, which cancels out with the squared portion of that. So we're going to get something in newtons per kilogram. And the number, if you do the calculator work correctly, is 9.8. Okay, and what is a newton per kilogram? Well, if you remember, a newton by definition is a kilogram meter per second squared. Kilogram meter per second squared. So a newton per kilogram would be a Newton meter per second squared divided by a kilogram. So that just means that the kilograms would go away and you get meters per second squared. And that is why this is equal to 9.8 meters per second squared. So there it is. We have calculated the theoretical acceleration due to gravity on the surface of the Earth, which is exactly what you get as long as you are dropping something with no air resistance. Finishing this out, letter F. If the Earth was suddenly placed 3 times farther away from the sun, what would happen to the force of gravity between them? Well, check it out. The force of gravity between the Earth and the sun is big G times the mass of the Earth times the mass of the sun divided by the distance between them squared. So if you increase that distance by a factor of 3, you would basically be doing this, throwing a 3 in front of that distance here. Now, the denominator is squared. So you wouldn't just be dividing the force of gravity by 3, but you would be dividing it by 3 squared. Okay? That means it would change by a factor of 1/9. So the force of gravity would be 9 times weaker if the distance between the Earth and the sun was tripled. So I'll just write that down here. F grav would change by 1/9 times its original, 9 times weaker. That's called an inverse square law, by the way, this relationship here, right? In the numerator, distance is inversely proportional, the force of gravity is inversely proportional to distance squared.